minutes to see if... Yeah, we're having some participants already connecting. I'm just going to give it one more minute, and then we can start. Okay, I think we can start already, so we don't delay too much the presentations. So good afternoon, everyone, and welcome to this CMCC webinar entitled A Primer on Atmospheric Inverse Modeling towards Greenhouse Gas Emission Monitoring using Atmospheric Measurements, organized in the context of the EU-funded project AVENGERS. I am Carolina Gallo, researcher on forestry and climate policies at the Impacts on Agriculture, Forests and Ecosystem Services Division of the Euro-Mediterranean Center on Climate Change, the CMCC, and I will be moderating the session. With me, we have today Sander Houweling, who is a professor in atmosphere, greenhouse gases and climate at the Department of Earth Sciences at Vrije University, Amsterdam in the Netherlands, and will be explaining to us what inverse modeling is. We also have Marko Scholze, who is a senior lecturer at the Department of Physical Geography and Ecosystem Science at Lund University in Sweden. He's also the AVENGERS project coordinator and will be talking further about this project that deals with attribution and verification of greenhouse gas and aerosol emissions. Before getting into the matter, please allow me just a few minutes to give you a quick introduction of the CMCC as host of this webinar. The CMCC has the mission to investigate and model the climate system and the interactions with society in order to provide reliable, rigorous, and timely scientific results to stimulate sustainable growth, protect the environment, and develop science-driven adaptation and mitigation policies. The center also aims to develop foresights and analysis of our future planet and society. It has 7 offices around Italy, connecting both public and private entities. And we count with different members and institutional partners, mainly Italian universities, but also some other research institutions. The center focuses on an interdisciplinary research, counting with 9 different research divisions, dealing with different climate science related topics, and you can see all of them listed here. We also have a supercomputing center located at the CMCC headquarters in Lecce with almost 25,000 cores, and is actually the most powerful computational center in the country. The center does as well a great deal of outreach activities, not only producing scientific articles, but also being involved in educational programs, organization of events, and other communication and dissemination activities for the general public, such as this webinar. And I will just finish these few slides with some housekeeping. The webinar is being recorded and then will be made available on the CMCC YouTube channel that you can access with the link you see on the screen. And if you have any other questions, you can always drop us an email. And also during the Q&A session after the presentations, for any questions you may have for our presenters today, you can write them directly on the Q&A section, or you can raise your hands and we will give you the floor. Now I will pass it on to our first speaker today, Sander. Please, the floor is yours. Thank you.
Yes, thank you, Carolina. I will share my screen with you. Yes, make it full screen. That should work for you, all right?
Yes, thank you.
All right. Good afternoon, everyone. In about 20 minutes, I will try to explain you about what atmospheric inverse modeling is, to give you an idea of how it functions and how it can be used. I expanded the title a little because it said a primer or a short intro on inverse modeling, and I added atmospheric here because we realized that there are many kinds of inverse modeling. Like, I mean, it's a very general term, but for the purpose of this presentation, we will specifically be dealing with atmospheric inverse modeling. And even the field of atmospheric inverse modeling is too broad. Because I should explain the context of what I've been talking about a little bit more, is atmospheric inverse modeling in the context of greenhouse gas emission verification. The use of atmospheric data to evaluate emission inventories that are maybe done on different scales, but usually in the context of a national emission reporting. And the verification here is in these double quotes, and it has a reason that it is often mentioned in this context as greenhouse gas emission verification. But in the scientific community, it also raises some questions about whether we can really call this verification or not. And this is something that we can return to in the end of this presentation. You will have a better feeling and idea probably to judge what this verification really means in the context of atmospheric inverse modeling. As well as the other point of evaluation of national inventory reports with atmospheric data. And often this is mentioned as an independent evaluation, and also in this presentation, we will address this, the independence of this evaluation and to what extent we can really call this kind of inverse modeling analysis an independent evaluation or not. To give you an example of the kind of inverse modeling that we're talking about is the plot on the bottom right, which comes from the National Inventory Report of the UK, where they report their national methane emissions. And as you can see, there's a chapter in this National Inventory Report that not only shows inventory values as the white bars in this plot, but also blue values, which is an assessment of the national methane emissions of the UK using inverse modeling techniques. And so they spent a chapter in their report already doing this kind of evaluation. And as you can see, for more recent years, it's a bit hard to see on the x-axis is time running from 1990 to 2018. The two approaches, bottom-up and top-down, they agree reasonably well, but it raises some questions going further back in time, which we will not address in this presentation, but it has also an indication of that these techniques are still in development. About then the general concept of atmospheric inverse modeling is depicted in this diagram, where you can see that emission inventories, they serve as a starting point for atmospheric inverse modeling. They are fed into atmospheric transport models as input, and these models are then run forward and they simulate concentrations of greenhouse gases in the atmosphere, as you can see here on the right. Those simulations then can be compared with atmospheric measurements. They can either be done on ground or using other techniques such as satellites. And these data, the simulations and the measurements together will enter an optimizer, which then seeks to adjust the emissions in a way that will reduce the discrepancy between the simulations and the measurements, minimize them, and brings the model in optimal agreement with the measurements by adjusting the emissions. And then the result of the inverse modeling in the end is an updated set of emissions that complies as good as possible with the atmospheric measurements. So a first ingredient, and an important ingredient that goes into this, are atmospheric measurements. And so you may wonder where they come from. An important source of atmospheric measurements in Europe comes from the Integrated Carbon Observing System, ICOS. Distributed over Western Europe, there are measurement towers, like the tall tower you see in this picture is the Cabau Tower in the Netherlands, where at a high frequency measurements are being made of greenhouse gases and other compounds. And it makes part of a wider network, as you can see depicted here in the map of Europe, where you see that the highest density of sites is in Western Europe. Besides greenhouse gas measurements of CO2, methane, N2O, and halocarbons, there are also other supporting traces being measured, not necessarily in the whole ICOS network, but there are other measurement initiatives by different laboratories to also deliver other types of measurements, as you see listed here. And their purpose is mostly to assist the emission attribution. On the one hand, we want to determine the amount of emissions, but we would also like to be able to attribute them to specific emission processes. And for that, these kind of other traces can be very helpful. In the context of European greenhouse gas emission monitoring and verification, there is in Europe the Copernicus program, which aims at setting up and developing this greenhouse gas monitoring system. This slide shows you a picture where on the one hand, on the left, we have the inventory work to compile all the emissions for the European countries. And to the right, we have the atmospheric system of atmospheric monitoring consisting of these tall towers where measurements are being done, as well as in more recent years also satellite instruments. And one example that I would like to show is the CO2M satellite, which is now under development and planned for launch in 2025-2026, a time frame consisting of 2 or 3 satellites to measure CO2 as well as methane from space. So then the question is, if you have these atmospheric measurements, then how do they relate to the surface emissions? This slide shows you a simulation of a model where the emissions are input in, and in colors you see total column CO2 as a satellite might detect it. And as you can see, the signal that is being measured is a combination of the emissions at the surface. You see some locations popping up, for example, here. I can maybe start the movie once more again. And those are mostly power plants in Germany that emit a lot of CO2. You see them as bright spots and plumes of CO2. But on top of that, there is also what we call CO2 weather. It's the movement of the atmosphere. And with the passing of fronts, the amount of CO2 that's being measured by the satellite also varies. So to relate emissions through their concentrations, you would not only need measurements, but you also need a very accurate model to simulate how the emissions translate to atmospheric measurements that are done either at the surface or from a satellite. So with these ingredients, then the question is, how do we then optimize the emissions? And for that, we need to discuss this funny creature that was in my initial diagram and how that exactly works. First, what we need to do is to find a measure of how well a model compares to measurements. And here I show a time series where in blue is a model simulation and in black you see measurements. And there are clear differences between the measurements and the model that we would like to reduce. And a measure of the difference between the model simulation and the measurements could, for example, be the root mean square difference between the two, as depicted here in this formula. Another probably the better way to do this is to also take into account the uncertainty of every measurement and then weigh the model measurement difference with this uncertainty. And so then the measure would become a root mean square error, summing all the differences between measurements and the models, weighted by the uncertainty of the comparison between the model and the measurement. So then, with that measure, let us take a very simple example of how one would do then an inversion for the case in which we have just only one measurement time series and only one emission. And then the equation could look like this. On the one hand, we have a CO2 measurement, and then which relates to an emission strength and time and a background concentration. And then suppose we have, at this location, we have 3 measurement points, and we can then fit a line through these 3 measurement points, like in a linear regression that would yield us with these coefficients A and B, which informs us about the emission that in this case will best fit the data. To do it in a better way, like I explained to you before, we should weigh this by the measurement uncertainties. And in this case, you see that the different measurements have a different uncertainty. And if then again we do this fitting, and I go back between the 2 lines, then you see that the line is now drawn to the measurements, or the measurement point here, that has a smaller uncertainty. So we put more trust in this measurement, and that's why in the end, the optimal fit to the data also comes closer to the measurement that we have more confidence in. Now, suppose another case, a more difficult case, where we have only one measurement, but want to fit 2 variables, A and B. And we know from mathematics that there are infinite solutions to this problem, and we are unable to find a unique solution. And this is a case that frequently happens in inverse model problems, where the solutions of the emissions that we are looking for are much more complex and have many more unknowns than the number of measurements that we have. So in practice, we are often in a situation that the optimization problem is underdetermined. And in that case, what we do is we add this a priori first guess model information. It means that we take an estimate as starting point with its own uncertainty, which in this case is taken quite broadly, in order to support the fitting of data that are in themselves insufficient to fully resolve the emissions. And in that case, we are able to obtain a unique solution that in this case is still close to this measurement because it was very uncertain. It had small error bars with respect to the error bars, the dotted lines here, that were assigned to the a priori model. So then to summarize how the inversion then finds an optimal solution is by quantifying a mismatch function. We call it a cost function, which adds up how the model deviates from the measurements, as well as how the posterior emission solution that we find deviates from a prior emission solution that we took as a first guess. So we want to minimize these both terms. We'd like the model to stay as close as possible to the measurements, but at the same time, we want a solution that is also close to the prior set of emissions that we prescribe. Then to find a solution, the posterior solutions of the inverse modeling exercise, we need a mathematical procedure to minimize a multidimensional problem, as in practice there will be more emissions and there will be more measurements. We need an effective search algorithm to find the minimum of this cost function. And there are various techniques like ensemble-Kalman filter or 4D VAR that you may find in literature, which are mathematical techniques for finding this minimum. The final part of my presentation deals with what this now means for the uncertainty of our emission estimate. And to explain you this, I will try to do it graphically because that makes it a little easier, starting again with the situation that we have one mixing ratio measurement and one emission on this axis. And we put these variables as random variables with their uncertainty distributions depicted here as Gaussian distributions. So if we have an emission with its uncertainty and a mixing ratio with its uncertainty, then we can define a joint probability distribution, because probability is here on the z-axis, which depicts then all the possible combinations between emissions and mixing ratios. Now we know that not all those combinations are equally likely or even possible given what we know about atmospheric mixing and transport, because that is defined by our transport model. And so if we draw the transport model in this diagram, here is a relationship between mixing ratios and emissions. So the higher the emissions, the higher the mixing ratio as defined by this model. So only this part of the probability density function that complies with this model is physically realistic. And that means that we can use this to narrow the joint probability distribution with these cross-sections of probable outcomes. And the final step in the inversion is then to project this cross-section of likely solutions back to their original axis, the emission axis as well as the mixing ratio axis, which gives us then the posterior likelihood of the emissions and of the mixing ratios. And as you see, the emission has not only changed, the mean has not only shifted, but the width of distribution has also become substantially smaller than it was a priori. So we have managed to reduce the uncertainty of the emissions in this process. With that, I'll come to my last slide and I summarize what I have explained to you. So the atmospheric inverse modeling is a method that brings the emissions from inventories in optimal agreement with atmospheric measurements. Then sometimes this is referred to as verification, but if this can be considered a true way of verifying emission inventories will depend on how well this works, how many measurements are available to really make it possible to do such a verification. Secondly, the method that I described is called the Bayesian method, which provides a statistical consistent framework to combine different pieces of information, like emissions and atmospheric concentrations. But how consistent the outcome is in practice depends very much on the statistical consistency of the information that is fed into the inversion. And it, for example, relies also on the information that is available on the uncertainty of the emission inventories. Thirdly, the solution that we find, as you have seen, is not independent of the a priori starting point. And that means that the outcome of inverse modeling is not an independent estimate per se. However, the atmospheric measurements that went into the analysis, they are independent pieces of information. Finally, linking to the next presentation, which is going to be given by Marko Scholze, applications of these techniques are investigated as part of the Horizon Europe AVENGERS project, and will then be further discussed what kind of applications there are in the next presentation. With this, I thank you for your attention.
Thank you very much, Sander. Very complete presentation and very interesting the work that you are doing with the models. We will give now the floor to Marko, and then we will leave the questions and answer session for the end. So Marko, please, you can share your screen and start when you're ready.
Okay, yes, good afternoon, everyone, and thank you, Carolina. For the introduction, I will share my screen. You can see
Yes.
the slides in full screen. Okay.
Very well.
Good. So Sander just gave you an introduction on how atmospheric inversion modeling or inversion model systems work in principle, and I will now take that a little bit further and give you an overview how we want to apply them in the AVENGERS project, and besides what we do besides atmospheric inversions in the AVENGERS project. Before I do that, let me start with giving you some facts, some basic facts about AVENGERS. It's a Horizon Europe project funded under the call on verification and reconciliation of estimates of climate forces. So that's from the Cluster 5, Destination 1, Climate Science and Responses for the Transformation Towards Climate Neutrality. It's a 3.5 years project, so 42 months, has started earlier this year and then runs until June, end of June 26. We have 16 partners now involved in the project. Out of these 16 partners, we have 4 national reporting agencies, or one entity, one institute who provides data for the reporting agencies. And I've highlighted them here in the list of the partners with this orange or beige color. So it's an agency from Italy, Netherlands, and Germany. And then in Sweden, we have this supporting institute. We have a total budget of almost 6 million euros. So 5 million from the Commission to start with. Then we have a Swiss partner who is financed by the Swiss government. And we have, I should mention that, we have on top of the original 14 partners, we have, actually we have 15 partners. I see that I made a mistake here. 15 partners. We have the 15th partner, which is a Cyprus Institute, which came to the project through a hop-on proposal. Under the same call, there are 2 other projects funded, which are called iClima and Paris. So we have in total 3 projects answering this call. And I will come back to that at the end of my presentation about AVENGERS. So the objective of the project is really to reconcile reported greenhouse gas emissions from the agencies, inventory agencies, with independent information from atmospheric observations using the top-down methods. So what Sander just explained, the atmospheric inversions, and process-based models aiming at reducing the most important uncertainties of national emission inventories. And that is one of the reasons why we have them as partners, so that these 4 agencies can help us, the atmospheric scientists, to guide where are the largest uncertainties and where are the biggest needs in terms of what they need to know and where they need to reduce uncertainties. So I've shown here in the diagram essentially that's the main objective I just mentioned, and then some more specific objectives around these this main objective. And these are essentially the source attribution of the emissions by atmospheric inverse modeling of greenhouse gases and aerosols. Sander mentioned that we not only want to know the total emissions, but also want to attribute it to the different sources, which is of course important to know for climate mitigation. We also do process attribution, and that's why we have the process-based models included and estimation of emission factors, and they're specifically focusing on forestry and land use. We prepare prior emission fields based on inventory data. So Sander also mentioned that an important ingredient to the inversions are these prior emission fields. So that's one of the specific objectives. Then, well, we work together with the national inventory compilers and collaborate to get the best possible prior emission fields. And as I mentioned before, to get to know where are the highest uncertainties. And then finally, we will produce guidelines on how to use atmospheric inversions for emissions verification, and produce also a flexible inversion tool which can be used by the national inventory compilers to play around with themselves. The project structure is as follows. We have in total 8 work packages. We have one work package 1, which is really dedicated to the dialogue with the inventory agencies to discuss what are the reporting needs and visions from the agencies, how we can support the reporting, and define specific case studies. Then, of course, we will do the reconciliation as well, and that is also done in work package 1. Work package 2 and 3 are really dealing with the modeling, the inverse modeling. So we have work package 2 focusing on the greenhouse gas verification, work package 3 on the aerosol, since we are not only looking at the major greenhouse gases, so that's CO2, methane, and N2O, but we also look at selected aerosols. That's essentially black carbon, organic carbon, and SO2 as a precursor for sulfate. So that's done in work package 3. Then work package 4 looks at the process attribution. I mentioned already the process-based modeling, land surface modeling, to really understand the processes behind the emissions and derive emissions factor, really focusing on specific case studies. Work package 5 is looking at future capabilities, so how the future observing systems will help to reduce uncertainties. And there, Sander already mentioned CO2M as one of the new satellites launched by the European Space Agency together with the European Commission, as part of the Copernicus program to develop this CO2 MVS monitoring and verification system. And then finally, well, we have a work package 6, which produces input to the international programs and derives the guidelines. And then finally, we have this work package 8. I mentioned already the Cyprus Institute, which is a hop-on partner. And there we are actually transferring what we've learned from the case studies defined in work package 1 to the specific environment of Cyprus and the Eastern Mediterranean and Middle East region. So what are our focus regions or case studies? So we defined the FLU sector as one of the most important sectors for the reporting. And there we will look at specifically at forestry for the case of Sweden. We will look at agricultural land use for the case of Italy and the Netherlands. Then we look specifically at Germany, which we thought is interesting because it's one of the largest, or it is the largest economy in the EU. And we have the reporting agency, the Umweltbundesamt, as a partner in the consortium. So we will look at Germany as a whole, not focusing on specific sectors. Then we have Switzerland as a focus, because Switzerland, together with the UK, are so-called front runners. So they are already supporting the national emissions reports by inverse modeling results, and that's why we have Switzerland. We have Cyprus and the Eastern Mediterranean, Middle East region. I mentioned that already. And then we will look at the EU plus UK as a whole. And there we focus in general on greenhouse gases and aerosols. I mentioned already that we have this SO2, organic carbon, and black carbon. And for the greenhouse gases, we look at CO2, methane, and N2O. Some science highlights. Sander already explained how atmospheric inversions work in general. We will further develop these and apply them as multi-tracer atmospheric inversion systems for both greenhouse gases and aerosols. And multi-tracer means that we not only take one species, or one observed species as an observational constraint, but include other measured species, such as, for example, NO2, which is also produced when burning fossil fuels. And therefore, when we take that into account in the inversion, we can then actually distinguish between natural emissions and fossil fuel emissions. The same, for example, for radiocarbon, 14CO2, for delta 13C and deuterium and alkanes, that it's rather used for methane for the source attribution for methane. And then we will do a joint black carbon CO2 inversion, again, for distinguishing between fossil emissions and natural emissions. I've listed here the different models we will use in the project. I won't go into the detail. It's just for you to see that we use different models and different inversion methods or data assimilation methods and apply various models to the various species. To look a little bit into more detail or to go beyond this atmospheric inversions, we will also apply a so-called coupled fossil fuel carbon cycle data assimilation system, where we not only invert the atmospheric transport, but also essentially the underlying process-based models to optimize parameters of these models, and then have a process-based understanding or improved process-based understanding. We will, I mentioned already, evaluate future infrastructures with both atmospheric inversions and this data assimilation system. And one of the main focus observing networks will be CO2M, the satellite system, but also the IAFES extension, and look at different settings of how the network might evolve. I mentioned we will look at emissions factor quantification for greenhouse gas flux estimation in the upper loose sector using process-based so-called DGVMs, dynamic global vegetation models. There we have two models within the project. We have the Orchidee model and we have the LPJ gas model, and they both include a process-based description of forest management. And we have a third model, which is a dedicated forest management model, which is called Houweling, run by the Swedish Agricultural University. And then the question is, how can we better estimate the CO2 emissions from forestry with these process-based models? Can we quantify methane emissions for the Netherlands from the organic and mineral soils using process-based models? And what is actually the contribution of the agricultural sector to the Italian greenhouse gas budget from process-based bottom-up models? So these are the three case studies we've defined for process-based modeling. We will compare the radiative forcing from greenhouse gas and aerosols. Therefore, we will use the Earth system model EC Earth to calculate the radiative forcing from the aerosol emissions for a given year and country, and set that in perspective to the radiative forcing from their greenhouse gas emissions, so CO2, methane, and N2O. We will develop this flexible inversion tool for inventory compilers to use, and in a way that also non-atmospheric scientists can apply it. This is essentially to help the national reporting agencies to understand how atmospheric inversions work and to be able to play around with a flexible and simpler version themselves. One of the first outcomes we have already in the project is the so-called TOPAZ methane source attribution tool. It's so far only based on forward modeling, so there's no inversion involved there, but it's taking emissions, feeding them into a transport model, and then transporting these emissions and comparing them to the actual observations in Europe using the ICOS observations. It's a web-based tool. It runs more or less online, so there's a delay of 1 day. So you can see here on the x-axis is time, y-axis is the mixing ratio of methane. The black dotted points, black points here, dots are the measurements, in this case for Cabal. And then the different colors here represent the contribution from the different sectors to the atmospheric CO2 concentration. And this is, I took this screenshot from the web page. Here you have the link to the web page this morning. So you actually can see the contributions from yesterday here from the different sources. And well, the data lags a day behind, so that's from the 22nd of October. So yeah, the This tool is online. The link is given here. So if you want to play around a little bit with that, you're welcome to visit the web page. Oh, sorry, that was one too much. On top of that tool, we of course have many more expected results. I will summarize here and give a few highlights. So I mentioned we will produce good practice guidelines on how top-down emission estimation systems can support greenhouse gas inventories and the global stock take. We will develop a flexible inversion tool for inventory compilers for demonstrating the strengths and weaknesses in estimating greenhouse gas emissions, made available to the national inventory compilers, including training events. So that's for them to better understand, especially the strengths and weaknesses. So what you can actually do with an inversion and what is interpreting the results from an inversion. We will look at observation-based estimates of greenhouse gases. Obviously, we will derive posterior emissions of CO2, methane, N2O, and aerosol emissions and their uncertainties for Europe as a whole, but with a specific focus on some selected case studies. That's Germany, the Netherlands, Sweden, and Switzerland, such that they can be used essentially as input in the respective greenhouse gas inventories. We will look at improved estimates of the uncertain emission factors, and they're focusing on the FLU sector for Sweden on the forestry using Orchidea and LPG gas, and for Italy on the land use sector using essentially a data-based tool. So using satellite observations on land cover and emissions. We will estimate the climate impact of national emissions in terms of radiative forcing, taking into account the radiative impact of aerosols and greenhouse gases and contrast them. So to see how much of the radiative forcing is caused by aerosol emissions and how much is by greenhouse gas emissions. And we will evaluate future observing systems, looking at both satellite and in situ data in terms of the potential to further reduce uncertainties. One of the, in my opinion, most important expected results out of this project is to gain a better understanding of how the different communities work together and what is really needed to effectively work together among atmospheric scientists. So I'm an atmospheric scientist, so from my side, together with the process-based land surface modelers and the inventory compilers, so that we bridge the different communities. And I think the emphasis here is on effectively work together to reduce the uncertainties in emissions. My last slide is to advertise the stakeholder workshop. And I mentioned already our sister project, Paris and iClima. We are, AVENGERS is organizing a workshop to discuss user requirements and future services with National Inventory Agency representatives later in November, and this is in coordination with Paris and iClima and the Copernicus CO2 MDS and their supporting projects, CORSO and CO2. The deadline has already passed, but I think online participation should still be possible. So if you are interested, you're welcome to register. Go to this website here and register there. There's a registration link on the website. And with that, I'd like to thank you for your attention.
Thank you very much, Marko. Very good overview of the AVENGERS project and what we're doing in the context. We have some questions coming from the chat, and I'm just going to check 1 second. There's one hand raised, Janci Jan. I don't know if that was a mistake or if you want to take the floor to actually ask something. Yeah, maybe not. Okay, so I'm going just to start with a couple of questions on the chat, and then I will give the floor to the hands raised. There's one question coming from Annunziata Chiacchiera that is asking if should the density and distribution of observations and the resolution of the simulation model be close? This question was for Sander.
Yeah, there is indeed a relation between the density of a network and in the end, the resolution you can expect to achieve on the emissions. However, there is a bit of a disconnect between the resolution at which you want to run your atmospheric transport model, because that also needs to resolve the atmospheric mixing processes well enough. And what often happens is that the resolution of the atmospheric transport model is actually a little higher than the resolution of the emissions that are being optimized by the inverse model. Yeah, so to answer your question, it has two aspects. And we need to make sure that we resolve the critical atmospheric processes. And in the end, of course, the resolution at which we can estimate emissions will depend a lot on the density of the observation network that we have.
Yeah, thank you, Sander. There's also another question.
I can quickly
Marko,
add,
please.
since that is actually one thing I briefly mentioned it, want to study in AVENGERS as well, where we have this future observing systems work package. And there we actually want to look at what the impact on the density of the network is on the estimated emissions and their uncertainties. So we will look at setting up a network with many more stations and then see how that impacts the emission estimates. So that is actually one of the questions we are looking at.
Yeah, thank you, Marko. Sorry for almost cutting you. There's also another question from Marco Fianchini. If this inverse modeling approach could be used to identify sinks other than sources of emissions? I think this question can be also for both of you.
Yeah, well, I can take it. I deliberately talk about emissions in the context of emission verification. But in principle, the method is general enough to estimate fluxes more in general, and a flux could then be a positive or a negative surface flux. So indeed, there's within the generality of the inversion method, there is no distinction between a sink and a source. A sink would just be a negative source.
Do you want to add anything, Marko? Maybe not needed.
No, nothing to add from my side.
Yeah, there's one hand raised now. Davide De Santis, if you want to ask the question directly, we can give you the floor, please.
Okay, do you hear me?
Yes.
Yes, very well.
Okay, many thanks for the interesting presentation and talks. And I was texting in the chat already, but okay, it's okay to say directly. I was asking about how the current CO2 satellite observation, for example, for the OCO emissions, can be useful for the comparison with the emission, or in general, do you think to use that product in the framework of this project, and how do you think to use it? I mean, I would be interested in some comments on this topic. Thank you.
I can take it, or Marko. I mean, I can start, and then maybe Marko can fill in. Yes. The OCO2 satellite is a very useful satellite indeed to investigate how to measure CO2 from space, and it started some years ago, and the measurement products have developed a lot ever since, and this is really an ongoing development where the challenge really is to make these measurements accurately enough from space so that we really add value and we can use it to support the emission quantification. And I think we are at the stage now where indeed useful information can be extracted from those satellites. However, to do this on say the national scale in Europe we believe would need sensors that have a better coverage than the OCO2 satellite can provide. So we need a higher density of data. And one of the reasons is that Europe is a difficult continent for satellite measurements because of the cloudiness. And the satellites need clear sky conditions. And so to have sufficient data, really, you need a satellite that has good enough coverage to make use of all the opportunities that arise in clear sky conditions. And that's why we're pushing very much for this CO2M satellite to be developed and launched, because that will then really enrich the data set a lot and provide us a lot more information that, in my opinion, is really needed to improve the constraints that can come from the satellite data.
I can add another aspect. Of course, I fully agree with what you said, Sander. And you briefly mentioned it. The problem with satellite data is that, or the problem, but one of the difficulties is that they have large uncertainties. And well, they are improving, but still having large uncertainties, and especially systematic uncertainties, systematic errors, which are caused by. So the satellites are actually measuring light only, right? Or absorption of light or photons. And whatever is in the atmosphere deteriorates the signal from the CO2, which also absorbs light. So, for example, clouds, Sander mentioned that, but clouds, it's not everything. The other substance or constitute in the atmosphere are aerosols, which are causing systematic errors in the CO2 retrievals, satellite retrievals. And one of the aspects of CO2M is to drastically reduce this bias by having a dedicated aerosol instrument on board, aerosol sensor on board, such that we can correct for these biases caused by aerosols, and on top of that, it's also the cirrus clouds in the higher atmosphere. So while OCO2 is already very useful, and as mentioned, the biases have reduced, but we think that with CO2M, we get to another quality of data with even much reduced uncertainties. And that is also what we need for the attribution on a finer scale.
Many thanks for your clarification. I was just guessing, we have to wait a few years before the launch of CO2M, and I was just wondering about the use of possible other satellite mission available, that they have maybe some limitations, but can be a kind of prototypes of study.
Yes.
I mean,
exactly. Yeah. No, we will definitely use the other missions which are flying already. So CO2 for methane, it's actually a bit better. There we have Tropomi, which delivers quite good data, and we will definitely use these observations, satellite observations, in our inversions. Yeah.
Thank you.
Thank you very much. We have plenty of questions. I hope we can manage to get some of them at least before the end of the webinar. And if not, you can always send us anything via email. So next question was from Julia Zazzeri. Could you please provide more details about the source apportionment of emissions using inverse modeling? Do you need tracers such as isotopes, or can we work only with concentrations?
Yeah, I've shown a list on one of my slides with some of those examples of tracers that can be used for emission attribution. And as you have seen in that list, there are indeed a couple of isotopes. And isotopes are, I think, the classical example of a measure and a metric that is helpful in attributing atmospheric signals to emission processes. But there are other examples also, like I can give you the example in the case of methane, for example. You could also measure ethane at the same time. And the ratio between methane and ethane is an indicator that emissions might come from the fossil fuel sector, because their methane is emitted also with a fraction of ethane. So these kind of tracer combinations can further inform us whether sources are microbial from agriculture, for example, or if they have a fossil origin. So it's not only isotopic information that can give us process information, but also combinations of other tracers that could be helpful.
The same is true for CO2. So that was the example for methane, right? But for CO2, we have the same thing. There we have what we call co-emitted species. So that is, I mentioned that briefly, that is NO2, for example, or CO is also a co-emitted species, which are produced when we burn fossil fuels. And coming back to CO2M, CO2M also measures NO2 in the atmospheric column, because it's a co-emitted species of the burning processes. And if we know that the amount of NO2 and have the emission ratios, know the emission ratios between CO2 and NO2, we can, by adding NO2 in the inversion process, also learn about the CO2 sources, especially about the fossil fuel combustion sources. So that would be essentially power plants. That's the main focus here, where we can reduce the uncertainties in the emissions from the power plants by adding co-emitted species. Yeah.
Yeah, thank you. We have also from Evelyn Riksen, when are we expecting to have the inversion tool and the guidelines available for the compliers?
Yes, unfortunately, both at the end of the project. So we are working on those. We started working on the inversion tool. We are in frequent contact, defining how we need to contact with the inventory agencies, which are our partners in the project, how to set up this tool. It should also be, it should not be only a tool to play around with, but it should also be somewhat useful for the agencies and produce realistic numbers. So that's why we are in frequent discussions about how to set it up, which greenhouse gas. So we agreed already methane is a tracer to go for, which region do we want to look at, and so on. But that takes, of course, a bit of time. So, and then developing the software behind it and so on, that takes a bit of time. So that will come at the end of the project in 2026. For the guidelines, we are actually discussing that at the moment with our sister projects, especially with the iClima project, because they have guidelines as a deliverable as well in their projects, focusing exactly at the same stakeholders, so the inventory agencies. And we are discussing on combining essentially our two deliverables into one from the two different projects, because we think it doesn't make sense to produce two sets of guidelines, which in the best case are saying the same thing, in the worst case are actually contradicting each other, and then that's not really useful. So we will produce one set of guidelines, and then we will also come towards the end of the project, because we want to include what we've learned during the phase of the project into the guidelines, and also refer back to the tool, if possible, on how to use that and include that in the guidelines. So 2026, summer 2026.
Yeah, that's correct. I think we have time only for one more question. It's from Robbie Morrison. Do projected mitigation efforts currently feed into this analysis, or maybe going forward?
I can maybe answer on the mitigation effort, not so much on the projected mitigation efforts, but there have been past mitigation efforts for which we are very keen to apply the inverse modeling technique to test if we can actually see evidence in the atmosphere that those mitigation efforts were effective. And an example that I can give you is for methane. There have been efforts in the past decades to reduce methane emissions from landfills. And as a result, the European emissions of methane in many countries have been estimated to go down in recent years. And we are very keen on applying the systems and studying this in more detail with all the atmospheric information that we have available to find evidence that the emissions indeed have gone down. And but this is for mitigation efforts that have already happened. Like those that are projected for the future, of course, are difficult to address with the measurements that we have available.
Maybe we have time for just one quick question that was actually posed before. How is it planned to get the results to the decision makers as quickly and effectively as possible? From Carla Schulte-Fischtek.
That's a very good question. I think that's why we have this kind of dissemination activities we are having today, the sort of this webinar. Of course, today was only to give you an introduction to the methods and to the project, what we want to achieve. But we will run at least another webinar, if not even more webinars, where we present results. And that is then focused to our stakeholders and decision makers. And I think, Carolina, if you want to add, because you are one of the task leaders for that activity.
Yeah, we're having actually like a plan on communication activities, and especially for the decision makers at international events, and we are coordinating that with all the rest of the work packages. So we are working on that thing. We will have as well a deliverable at the end of the project, and yeah, like we, as Marko said, also trying to do some of more general public events such as this one, and going probably for not this year because it's still a bit early for the project, but also going to COP and presenting this type of things to the decision makers. So yeah, that is part of our plan. I'm so sorry, but we have two questions that we're not going to be able to answer live because we're already like a few minutes over the time. Please send us your questions if you want via email. You have our contacts. If you rewatch the presentation on YouTube, in all three presentations, Sander, Marko, and my emails are there. So if you want to contact us, please feel free to do it. And I think I'm going to close here. I want to thank you both, our speakers today, and all the participants for the questions and very interesting discussion. Hope to see you soon then. Thank you, everyone.
Yep, thank you also from my side.
Thank you. Bye-bye.